Hello again. Well, pick up here's what we're up to today. Pick up where I left off in section 8 at the end of the last video. And then I think we'll get partway into section 9. If we went on the original schedule, probably something like half of Monday's class would have been taken up by the quiz, which wasn't there. So that kind of gets me ahead, which is fine. Ahead, there is nothing in the world wrong with ahead. If you don't like being ahead, you can just wait to play the video. I'd record the whole course today if I had time to do it. The handout for sections 9 through 14 is here. One way that a video course is not quite the same as being face-to-face is I can't quite hand out the handouts to you, but hopefully by the time Friday gets here, they'll still be letting us meet and I'll be able to give that to you. If not, well, go into the website and you can, all the handouts for this course are in the website. You can go in there and read it off the screen or maybe print off a hard copy of it for yourself if you want to. Well, I should start actually doing something. The first thing I hadn't gotten to last time was problem number 6, which dealt with the same situation as problem number 5. I'll just kind of slide this over here. So in both of these problems, there are 2 parallel wires. And looking at it from the end, okay, if you take the picture that's in the handout there, and if you turn the thing so you're looking at it from this angle instead, what you see is you've got what I call the wire C carrying current out toward you, and down here we've got wire D, which carries a current away from you and me. And as I explained when I was doing number 5, the Y direction would be that way, the Z direction would be that way when you're looking at things from this point of view, because the XY plane was the plane of the original picture that appears in the handout there. So this time what it asks me to do is find the force on this wire, which happens to be in this direction. Well, actually, that's the magnetic field. Let's take it a step at a time. Yeah, the force would be that way, or actually that way. But I'm getting ahead of myself. It's a 2-step process. What this is I think the last lab you did before we had the break was the current balance lab. And the calculations for that lab are exactly what this is. The lab had gotten a little bit out ahead of the lecture at that point, although not far enough that it was a problem or anything. But as you may remember from doing the lab, it's a 2-step kind of thing. Step 1, you have to figure out the magnetic field created by this wire. Once you know that, step 2, what is the force on this wire as a result of being in that magnetic field? Well, for the direction of the magnetic field, remember, magnetic field lines circle around a straight wire, and they do that in a right-handed direction. So if the current, what you do is, if this is the wire, you grab the wire with your right hand, such that your thumb points in the direction that the current is going. And your fingers wrap around the wire, pointing in the direction of the magnetic field. So that would be down this side and across the bottom and up the other side. And what we're actually interested in is what is the direction here where the other wire is located. Well, from the right-hand rule, field lines circle around in that direction. A tangent to that circle at this point would be in the negative z direction, like that. So at this location, the field due to wire C points in that direction. For its magnitude, the field of a straight wire is E equals mu naught I over 2 pi r. I showed near the beginning of section 8 how that follows from Ampere's law. You take Ampere's law, you apply it to this special case, and that's the result. If you don't happen to remember, you look up mu naught, and it's that. I is the current in wire C. We're finding the field of wire C, so this current should be the current in wire C, which is 10 amps. And the point where we're finding the field is a centimeter away. The location of the other wire is a centimeter away. So two Gausses, 0.000, 3 zeros and a 2 of a Tesla. So that's the magnitude and direction, and we're halfway through the problem. Then force on wire D, due to being in that magnetic field, would be, and this goes back to section 7, the force on a current carrying wire is IL cross B. If we're calculating the force on D, then this would be the current in D, which is 7 amps. The length vector. Well, it says that each wire is 1 meter long. So 1 meter for the magnitude. For the direction, the length vector points in the direction that the current flows, except I shouldn't have said the direction the current flows, because current's a scalar, it doesn't have a direction. Went through all of that before. It's flowing away from us. Well, maybe it's clearer in the picture that came with the original question. If you look at the picture on the note packet I gave you, it shows that that 7 amps is flowing in the negative x direction. So for my direction vector, I've got minus I. And then the magnetic field vector is what I just got done figuring out. That's negative 0.0002 K. And then we just have to evaluate that. Minus signs cancel. So we've seen a couple like this before. It's two separate things to multiply. You've got numbers to multiply, and I guess I can fit that in down here. 7 times 1 times 0.0002 gives me 0.0014 of a Newton. So there are numbers to multiply and there are vectors to multiply. We have I cross K. I cross K is equal to, drew that really badly. Let's try that again. Negative J. And there are different ways of coming up with that, but probably the simplest thing is if you remember the little circle thing where you just go I, J, K like that. And this was I cross. So you start on I cross K, you end up on the J, and you went around in the negative direction. So I cross K is negative J. So tying it all together in a pretty little package, the answer is negative 0.0014 J. It's a force, it's measured in newtons. So if I make a little sketch, here's the wires. Remember, it was the force on the bottom wire that I'm calculating. It turned out to be this way, the negative Y direction. If there was a part B to the question, which there isn't, but I could have just as easily done that, it would, if the part B was what's the force on the other wire, well, there's a long way and a short way. The long way is you could go through all this sort of thing again, find the magnetic field from this wire, and then calculate IL cross B for that one. Or the quick way to the answer is just say Newton's third law. If C pushes on D, D pushes back on C. It's an action-reaction pair. It would be the same number of newtons in the positive J direction is the force on this other one. The wires repel each other, just like in the current balance lab that you did. If the currents had the same direction rather than opposite directions, they would attract rather than repel. Top of the next page. I slipped this in the notes, I don't know, not too long ago, a couple of years or something like that. Because a student had a question, and I figured, well, you know, maybe I should explain that to everybody. So this is just variations on the same thing that problem number 6 illustrated. In the problem I just went through, we saw how that this wire is repelled from that one. The X's are the magnetic field coming from this upper wire, you know, right-hand rule. And then when you cross that B vector with this L vector, you get a force that pushes that way. Well, let's move over to, instead of some straight wires, let's have a pair of coils, okay? Well, a section of wire along this coil is pretty much the same thing as what we had here. It curves a little bit, but just like before, there would be a downward force on that wire. Of course, a section of wire up here is similar to the wire up here carrying the current in the other direction. So that shows how that a pair of coils, maybe solenoids, long coils, repel each other just like these two straight wires repelled each other. Now, if you want to talk about magnetic poles, remember one way of stating the right-hand rule is that if you grab the coil with your fingers wrapping around in the direction that the current flows, your thumb points, one way you hear it phrased is that your thumb points north, okay? The north end of this solenoid is beyond the edge of the picture up here somewhere. This would be the south end. Same thing with the other one. The north end would be down beyond the end of the picture somewhere. This is the south end. So we have here two magnets. A coil is just an electromagnet. We've got two magnets who we've brought like poles together. South repels south, just like with electrostatics, minus repels minus. If you want to take it one more step, you could talk about permanent magnets instead of coils. Well, south still repels south. I don't think I got to this part yet, but it's coming up fairly soon. Where the electric currents are in a permanent magnet is at the atomic level. You've got the electrons orbiting around the nucleus, which are little tiny loops of electric current. And you have the spin of the charged particles inside of an atom. And if you picture a rotating electrically charged sphere, like an electrically charged basketball spinning around on the end of somebody's finger, there again, you have charge circulating around, you know, it's current loops. And so you don't see the currents in the permanent magnet because they're on a very small scale, too small to see. But it's a variation on the same thing that's going on with this pair of solenoids here. So it's all just variations on the same basic idea. Well, it looks like there's another problem for me to go through a little further down the page there. Problem number 7. You've got an electron inside of, as long as the camera's pointed at it, I might as well just move things up a little bit. Somewhere inside that coil, I guess it's a big coil and there's a small vacuum tube inside of there. And inside of that tube, there's an electron going toward the left. And we're supposed to find the force on it. This is actually just a minor variation on the one that I just went through. Back here in number 6, well, with number 7, it's the same two-step process. Step 1, find the magnetic field, only now it's going to be the magnetic field of the solenoid instead of the magnetic field of a straight wire. So it's a different formula to find B. But aside from that, it's the same sort of idea. Step 1, find the magnetic field. Once you know the magnetic field, find the force on, well, this time it's an electron instead of a wire. So instead of IL cross B, it's going to be QV cross B. But, so, you know, details are different. Big picture is pretty similar. Step 1, find the field. Step 2, find the force on something because of being in that field. So that's the basic idea, and the details go like this, or they will in a few moments anyhow. The magnetic field of a solenoid, mu naught I N over L. I think that was the second example that I did from Ampere's law near the beginning of this section. Four pi times 10 to the negative 7. There's no escaping from that number as long as you're talking about magnetism. Coil carries 8.1 amps. And it has 1,000 loops. .2 of a meter, 20 centimeters. The length of the coil was labeled on the diagram. Crunch the numbers and .0509. Measured in Teslas. That's the magnitude of the field. To get its direction, well, remember the field of any coil is along the axis, okay? The field inside of it anyhow. So the axis of this coil runs along the y-axis. The coil goes up and down. The right-hand rule is to choose between the two alternatives. Does the magnetic field point up the y-axis or does it point down the y-axis? You grab the coil with your fingers wrapping around it in the same, pointing in the same direction that the current flows, okay? The diagram looks like the current goes toward the left, or I'm sorry, toward the right, whatever side of the page that is. The current goes toward that across the front of the picture and then returns the other way around the back. So the current goes around the coil that way. Looks like my thumb is pointing in the positive y direction. And so the B vector is B with the arrow over the top this time, 0.0509 J Teslas. And once again, the way I got the direction for that is that the magnetic field goes along the coil's axis right-handed. Then there's an electron in that magnetic field. A charged particle moving through a magnetic field feels a force of Q V cross B. An electron has a charge of negative. Don't forget the minus sign or you'll end up reversing the direction of your answer. Negative 1.6 times 10 to the negative 19 coulombs for Q. The velocity vector question says it's going toward the left, meaning the negative x direction, at 2.3 times 10 to the 7 meters per second. And we cross that with the magnetic field vector that I just got done determining. Minus cancels minus. We multiply the numbers And those three numbers multiply out to 1.87. Ten to the negative 13 newtons. As for the direction, well, I still got my little circle drawn back over here. We have to do I cross J. So start here. I cross J is K. And I went around counterclockwise, which is the positive direction. So it's a positive K. So 1.87 times 10 to the negative 13 K newtons. And then the last thing that I've got in section 8 is some more practice for you using the right-hand rule, because that seems to be the thing that gives students the hardest time in this section. So if this was a regular class, I would stop here and tell you to think about those for a couple of minutes. After about 3 or 4 minutes, I like to go over part A and then give people, you know, because maybe people don't know what they're supposed to do and they've seen it done once, maybe they can do the rest of them after that. So I usually do part A and then I stop for a few more minutes and then do the next couple parts and so on. So I'm just, you know, I'm just going to go right through this, but pausing the video can be your job, okay? So why don't you stop it now for a moment and figure out what you think the answers are, because like I've said before, doing something active, you're going to learn more than just sitting there and being passive. I think it'll stick with you better and you'll understand it better if you do it wrong, and then I explain to you how you could have done it right, than if you just go right straight to the part where I explain it to you. It'll make more of an impression if you try it yourself first. So anyhow, somewhere around here, you unpause it again. And the answers, well, why don't I just write out all the answers and then go back and do the explanations. So there's, first of all, across the first part of the question, there's an A, a B, and a C. The answers are that in part A, you know what? Before I give away the answer, let me make sure everybody understood the question, because there have been questions about this sort of thing before. Well, maybe it'll show up better if I just sketch it over here. But you've got a wire carrying a current that goes in that direction. And then there's, this thing is supposed to look like some sort of an electrically charged particle, an electron or a negative ion or something, whose velocity is in that direction. And in case you didn't figure it out, the idea is that it's like you've got this wire in the plane of the blackboard, and this charged particle is maybe an inch above the blackboard, moving along like that. And the picture captures the moment where that charged particle is passing over the top of the wire, okay? So if you didn't get that before, pause the recording here and see if you can figure out the answer now. But the answer is that for part A, there is no force. And in part B, the answer is that the force is in the negative y direction. and that in part C, it's in the plus X direction. And here go the details. In part A, well, the velocity points that way like I already drew. The magnetic field from the wire, remember how the right-hand rule works. The pencil here is the wire. You grab the wire with your right hand, with your thumb pointing in the direction that the current is flowing. Your fingers wrap around the wire like the magnetic field. So with the current going toward the right, that means the magnetic field comes up the back of the wire, over the top, and down the front, and circles around that way. Well, we're interested in what the magnetic field is doing in front of the wire, where this electron is. And right there, the magnetic field points downward. Like that. Well, QV cross B, that means QVB sine of the angle. That these two arrows, when you stick them together, they make a 180-degree angle. So the sine factor kills it off. You don't have to worry about any of the rest of it because it's all multiplied by 0. Without even getting into any formulas, I've mentioned before, magnetic forces on electric charges are greatest when the charge cuts directly across the field lines. When the charge goes along the field lines, there is no force, okay? And that's what's going, well, it's anti-parallel rather than parallel, but it's still, at this particular moment, it's moving right along the field lines around this wire, and so there is no force. For part B, well, this is like we're looking down, we're either looking down the throat of a coil, or maybe it's just a single loop of wire. The picture's unclear about that because it doesn't matter anyhow. The answer would be the same either way. Just like these other problems I did earlier, it's a two-step process. I'll have to use the right-hand rule twice. Step 1, what is the direction of the magnetic field? Step 2, once you know that, what's the direction of the force? So for the direction of the field, if you've got a current going around counterclockwise like that, you get your right hand, you grab the coil with your fingers pointing in the direction the current flows, and your thumb points in the direction of the field inside that coil. So from a counterclockwise current, you get a field in the positive Z direction. If the current had been clockwise, that would be a negative Z. Just like any other time, we used the right-hand rule all the way back to when we did torque in Physics 131, counterclockwise positive, clockwise negative. Once you know that, B points that way out of the blackboard. The velocity vector points that way. Possibly it might be helpful to make a little model out of pencils and pens. Or maybe you just want to skip that and use the little circle with the I, J, and K in it. But if you're going to build a little model, B is that way, V is that way. And so the cross product, V cross B, has to be perpendicular to both of those things, which means it's either plus or minus Y. To choose between those, wrap your fingers around the y-axis, pointing from the first vector toward the second. V cross B points up. So yeah, I did that wrong. If I felt like editing it, I would go back and you'd never know I did that, but I'm too lazy to edit the video. V is this one. V cross B. Thumb points down. Yeah, I was for a minute I was thinking this one was V, that one was B. Anyhow, I had it all messed up. So V cross B, fingers point from V toward B, and my thumb points down. Okay. Then the last one, we've got a current carrying wire. Well, last one in this group. Right hand rule. You grab the wire with your thumb pointing in the direction the current flows. Your fingers wrap around the wire, pointing in the direction that the magnetic field lines loop around there. So that would be out of the blackboard on this time, on this side, it arches over the wire and goes back into the blackboard over here. Well, over here is where our charge is. That's what we care about, is what's the direction of the field there. And the direction of the field there is through the page away from you. So then we've got a charged particle headed in the positive y direction. There's the B vector pointing away from you. The V vector is in that direction. So let's see if I can get this right the first time this time. B points away from me. V points up. No, I'm not getting it wrong. V cross B. Okay, I wrap my, it's got to be plus or minus X because that's perpendicular to both of these. V cross B, you wrap your fingers around pointing from the first vector toward the second one, and my thumb points left, but I should probably write that down, take this a step at a time. But it's a negative charge, there's a little minus sign on the picture of it there. So Q times V cross B would point the other way, which is positive X. The minus sign on the charge reverses the direction. So that takes care of those three. And if this was a real class, I would pause here and give you another couple of minutes to think about these last couple of questions. But again, just pause the video and when you think you've thought about it as much as is helpful, start the video up again. The answers here are that for part A, the negative X direction, and in part B, there is no force. And the explanation is same sort of two-step process. I've got a loop of wire. This time, the current is going around clockwise, which is going to create a magnetic field that points away from you. Over here, counterclockwise was positive. Over here, where I haven't pointed the camera yet, the current goes in the opposite direction. The magnetic field that it creates points in the opposite direction. And after that, there's the B vector. We've got a wire that runs along the y-axis. Current's headed toward the top of the page. So that's the L vector. L cross B has to be perpendicular to both of these things. So that's either X or minus X. L cross B, you wrap your fingers around the X-axis from L toward B, and my thumb points to the left. And this time we don't have to worry about whether Q is positive or negative. I is just a scalar. And well, scalars can be negative, charge is a scalar, but current is always positive. Anyhow, well, current, positive current. Anyhow, thumb points to the left and negative X is the answer. For the second part, I don't know if I need to draw a lot of stuff here, but the magnetic field of a coil points along its axis. You can use the right-hand rule to show that it points toward the right as opposed to the left, but it doesn't matter. The answer is going to be 0 either way. You know, if you reverse the direction of the current in this coil, the force is still going to be 0. So you've got that for the B vector, and going right up along the axis of the coil is this wire whose length vector is also toward the right. So it's that same sine theta factor that caught us at the beginning here, the first, part A, and QVB sine theta. Sine is 0 degrees. You take those two arrows, you stick them together, they make a 0-degree angle. And so QVB times nothing gives you nothing. And that is the end of section 8. And if I stick to 55-minute periods, which I don't necessarily have to, I suppose, but it looks like we've got 10 or 12 minutes to get started on section 9. And like I said, I'll get you the handout, assuming we're able to meet on Friday. Who knows what could happen between now and then. The Martians could invade or something, the way things are going. But if you can't get a physical hard copy, look at the website. There's a PDF of it. No, you focus. Not exactly, no. It's legible though. Okay, all that time I was fooling around, I thought I had the recording paused, and apparently I did not. So sorry about the dead time there. Anyhow, we've got, maybe I should edit these, but that sounds too much like work. This is the first page of section 9, and it introduces the idea of electromagnetic induction. So start out with a point of view that builds on what I'd already been saying in the previous section. Well, as a specific example, let's let's say you've got a loop of wire spinning around in a magnetic field, which is the basic idea behind a generator, okay? Of course, any sort of reasonably effective generator doesn't have one loop of wire. It's got a coil with hundreds or thousands of turns in it to create a larger voltage. But let's go for the simplest case, just one loop of wire to give it a way to spin around. Let's say it's been hung by a thread. You can wind it around a few times, and then when you let go, it's going to spin back the other way. I included a voltmeter so we had some way of detecting the presence of any induced voltage, but well, ignore that for the moment. Let's just say you have a loop of wire. Now, I just got done going on for like hours about how when charged particles move through a magnetic field, they feel a force. Well, the free electrons inside that loop of wire are charged particles, and as the loop of wire spins around, they are charged particles moving through a magnetic field, and they feel a force to the side, which will make them want to flow around that loop. So the QV cross B force pushes on them, and there'll be a current flowing. It's called an induced current when there's no visible source of EMF in the circuit. You've just simply got a loop of wire. It could be a coat hanger, well, except coat hangers aren't shaped like that. But aside from that, there is no obvious battery or other voltage source that you can, point at or stick in your pocket or something like that. And yet a current flows. So it's called an induced current when that happens. And this way of looking at it kind of builds on what we've already done, but it's not the way people usually look at this. Because rather than talk about forces that are too small to measure on electrons that you can't even see, and their velocity, you can't measure that really conveniently. Wouldn't it be nice to look at it in terms of something that you can measure on a $15 or $20 meter? Talk about an induced voltage in the loop rather than the forces on the individual electrons in there. So I wrote out this justification. I didn't want to spend a lot of time on it. It was, rather than write it all out on the blackboard and spend 10 minutes explaining it, what I wanted to do is say, oh yeah, see that right there? Well, let me just summarize this. So let's see if I can keep this down to about 30 seconds. But the induced EMF, well, EMF by definition is the work done per unit charge. It's voltage, in other words. From Physics 131, work equals torque times angle. If the loop chain turns, of course, we have to keep it down to a differential angle because angles and things, the angle between the area vector and the field is constantly changing as it rotates. So let's consider just a tiny little amount of rotation d theta. Torque from not that long ago is mu cross B. Mu is the magnetic moment and B is the external field, magnetic moment of the loop, which is equal to I times A, the current in the loop times the area of the loop. Current, by its definition, is dq dt, the derivative of charge with respect to time. The dq's cancel. And I rearranged a little. I recopied the B there, I recopied the A there, I recopied the sine of theta, and I put the d theta on top of the dt. Well, d theta dt, this over here is equivalent to that because the magnetic, at least in this example, okay, which is meant to be more illustrative than a rigorous derivation, but this is permanent magnet. I mean, it's like there's some big horseshoe magnet, most of which is beyond the edges of the picture, but the poles are bent around and they face each other, and in between there's this magnetic field, and it's a permanent magnet. So B is unchanging. It's a constant. The area enclosed within the loop is unchanging. The thing doesn't grow or something as time goes by. The only thing that is a function of time is the angle theta between the area vector and the, incidentally, we've talked about area vectors before, but I've already said, like when we did Gauss's law, the area vector is perpendicular to the plane containing the area, but a little more specifically in a case like this, it's right-handed. Your fingers wrap around the loop of wire pointing in the direction that the current flows, and your thumb points in the direction of the area vector. So anyhow, theta is the angle between the area vector and the B vector. It's the only thing that changes with time. The derivative of cosine theta would be, well, the derivative of negative cosine theta would be sine of theta times d theta dt. This part comes from the chain rule. So BA cosine theta, that would be the dot product of the two vectors. This has sort of a familiar feel to it. B dot A. I think you can read that. It looks a little on the fuzzy side on my computer screen here, but E dot A was electric flux back when I was talking about Gauss's law. Well, this would be the magnetic counterpart. B dot A would be magnetic flux. And so once you substitute that in, this says that the EMF induced in that loop of wire is equal to the time derivative of the magnetic flux, d phi dt. And I have some details to write on the blackboard, but that's the general idea. And that's basically what's called Faraday's law of induction. Let's see, where's a good place to write? Probably over here. I'll get that squared away, and I think that'll be about enough for today. So, section 9. First thing is to introduce magnetic flux. As with electric flux, the symbol is a capital phi. Put a B subscript on it for magnetic, but quite often you can tell by the context whether you're talking about electric flux or magnetic flux. So a lot of times I might leave the subscript off. Assuming a constant field, it's B dot A. The unit that flux is measured in is called a Weber. The relationship to other units we've already looked at is that 1 Tesla is equal to 1 Weber per square meter. B equals phi over A. The strength of the field is the flux density, okay? I think I've mentioned that before, maybe back when we were doing electric flux, but in a picture, the field is strong where the field lines are close together, and the field is weak where the field lines are farther apart. And how many field lines pass through a given area is how you represent the flux in the picture. So the field strength, the B vector, is the flux density, the flux per unit area. More generally, if the field is not constant, either in magnitude or in direction, You have to take the surface you're talking about, how much flux passes through some surface, like the surface included within that loop. In that example at the top of the page, you got a circular loop. What's the area enclosed within it? You have to divide that surface up into a lot of little dA type pieces. Integrate over the whole surface. Integral of B dot dA. So it would be like, if you've got, you want to know how much flux goes through this entire area, you have to subdivide it into many little pieces. And for example, for that one right there, that's supposed to look like an arrow sticking straight out of the blackboard. I don't think, I probably I'm not sure I succeeded at that, but that would be the dA vector for that little piece of the total area. B dot dA is the flux through that small area. And then you sum, you integrate over, add up all the flux from all the pieces to get the total. So I just have a couple more things I want to write, but I guess I have to make a little more space. So from what it showed on the handout there, the EMF in a single loop of wire. Okay, so referring to what's on the printed notes, the note packet, it showed that the EMF in a single loop was the derivative of the flux. If you have a coil with 100 loops in it, that much voltage is induced in each of those 100 loops. The total voltage in the coil would be 100 times that. So in a coil with N turns, induced voltage, the EMF, minus N times the derivative of the flux. And that is one form, at least, of Faraday's law of induction. And now that you've been introduced to Faraday's law, in the next lecture, we'll get into some of the details, but I think that's enough for now.